Alright, let's look at the second order reducible differential equations. So this is a second case when x is missing from the equation. So f of y comma y prime comma y double prime is equal to some constant c, right? So here's an example, right? So as usual, we're going to do this substitution. So I'm going to let p be y prime, right? Then I'm gonna try to figure out what y prime is. So y double prime is going to be, right? So this is just a derivative. So we're gonna take the derivative of p with respect to x, right? But instead, since I'm going to try to get rid of x, I'm going to take the derivative of p with respect to y instead, right? Then multiply by dy over dx, right? So dy over dx is just y prime, so which is p. So this guy right here is simply p. So that way we can write the y double prime as p times dp over dy. So we can write in terms of a derivative with respect to y, right? So let's rewrite the equation, right? So here's the original differential equation, right? Y, we're going to keep it as it is, right? Then y double prime is p, so it's going to be a p times dp over dy, right? And plus y prime, which is p squared. So p squared is equal to 0, right? So if you divide this guy through by, say, yp, so I'm going to divide through by yp, then you see that you have dp over dy, right? And plus, right, one of the p cancel out, so you're going to have 1 over y p is equal to 0, right? So this is either a separable equation or you can look at it as a first order linear equation. I'm going to look at it as a first order linear equation. So I'm going to do integrating factor. So integrating factor I is going to be, right? So remember that here, this is going to be our the notation is kind of bad, so this is a lowercase p, so this is going to be uppercase p, so it's a p of x. And the right hand side is, as usual, capital Q of x, right? So integrating factor is e to the integral, and we have a 1 over y, so that's p of x, and with respect to y, because this is a derivative with respect to y. Right? Then you have a e to the natural log of y. Then you can cancel e and natural log, so you end up getting simply y. Right? So we find the solution p in terms of y. So p is going to be equal to, right? Remember, it's a 1 over I, so it's going to be 1 over y integral, right? And the q of x actually is 0, so it's a 0 times I, which is y, which is going to be 0 anyway, dy, right? So what you get is, integral of 0 is just a constant, so you're going to get some constant. I'm going to call it the c1 over y. Alright, so now remember that the p is originally y prime. So we're going to get dy over dx, and which is equal to c1 over y. Alright, so this is now a separable equation. I'm going to multiply both sides by y. Then you will get y dy over dx is equal to just a number, c1, right? Then we can just, once we separate them, we can just integrate with respect to y, right? So we can cancel, oh actually, sorry, this with respect to x, that's what I meant here. So with respect to x here, and here, right? Then we can cancel dx on the bottom, dx on top, and then antiderivative y would be y squared over 2, right? And this is equal to, right, so you have a c1, so antiderivative is c1x plus c2, right? Then if you want, you can leave it like that. And one way to write that would be solve this equation for x instead of y, right? So we have, actually, maybe this might be cleaner. So I'm going to multiply through by 2. So you get y squared is equal to, right, and multiply by 2, 2c1x plus 2c2, right? So there's no point of using a complicated expression for just an unknown constant. So I'm going to call this guy A, and I'm going to call this guy B, right? So therefore, I'm going to write the solution as y squared is equal to ax plus b. All right. So that's the solution, written sort of implicit form, but this is a solution of the given second order reducible differential equation. All right. That's it. I hope that this was clear.